This is 20-2, Unit 1, Radicals Review. Unit 1, Radicals Review. So we're going to go over the first few outcomes that we need to remember. And one of the first outcomes is we need to be able to order radicals on a number line. Okay? So order radicals least to greatest. That's also called ascending order. On a number line. Okay, so that's one of the first things we need to do. Okay? You need extra paper. I do have extra paper up here too, if you're looking for some. Okay, you can come up and grab some paper there. So we need to order them least to greatest. So we have two strategies we can use to order radicals. Who remembers what one of the strategies is? Beautiful. So first strategy is convert to decimals. I think that's the one that takes the least time. It's probably the quickest way. The next one would be to convert them all to entire radical form. Convert to entire radicals. And once you've got them into entire radicals, all you've got to do then is the numbers under the radical sign, put them smallest to biggest. Okay? So there's two different ways we can do it. So I'll give you an example. You guys can write them down, and I'll give you a couple minutes to order these in order. Now the same goes for if it's a square root, or if it's a cube root, or if it's a fourth root, or a fifth root. We typically deal with square roots and cube roots, so those are what we deal with most. But you will see fourth roots and fifth roots. Okay. So, examples. We're going to order these. 4 root 3, root 43, 2 root 10, 3 root 7, and 2 root 11. So there's 5 radicals there. We're going to turn them all to decimal form because that's the easiest way. And we haven't reviewed how to turn to entire form yet. So we're going to go to decimal form first. I'll give you a moment to write that down. We're going to grab our handy dandy calculator, and we are now going to punch the buttons. We're going to convert them all to decimal form. So we're going to type in 4 square root 3, enter, and it's going to give us 6.93. 2 decimal places is a more accurate answer, so 6.93. So this guy, 6.93. Perfect. Now we get to the next one. We're going to go square root 43. 6.56. Who's got the next one? 2 root 10. How big is 2 root 10? 6.3. 6.3 what? 32? Okay. Who's got 3 root 7? 7.94. Okay. 7.94. And who's got 2 root 11? 6.63. All right. So now we're going to look at those decimal numbers, and we're going to think who's the biggest and who's the smallest on the number line. Okay? So, thinking a number line, I'm just going to draw one actually. And we've got 5 numbers. And what I'm going to do is I'm going to label them A, B, C, D. That's going to be easier for us than actually drawing the numbers. So, I'm going to label this guy A, B, C, D, and letter E. So, who is the furthest on the left? Who would be closest to 0? 2 or 10? You're exactly right. Letter C. So, this one right here is the smallest. So, it's going to be the one that's closest on the left. So, we're going to put letter C over here. Okay, letter C goes on the left. Who would be next to him? Yep, absolutely. Root 43 goes next. Cross him off. We did him. So B goes next. All right, who's bigger than B? Letter E is. Good job. Okay, so we've dealt with letter B, C, and E. Who's bigger than letter E? A is for root 3. Oh, that's cool, eh? There's A. And who's bigger than A? Last one, D. All right, not 7.94. He's pretty big. He's way bigger than the other guys. Okay, so that's how you would order them on a number line, left to right, smallest to biggest, okay? I'll give you a moment to copy that down. Okay, the next outcome we need to take a look at is converting radicals. So number 2 is going to be to convert radicals. So we need to be able to go into mixed to entire and entire to mixed. We need to remember what they are. So we're going to go entire to mixed first. Okay, that'll be A. Entire to mixed. So we're going to take a couple entire examples and we're going to mix. So I'm going to take example 1. Square root 45. Now, when we are reducing radicals, what we do is we divide them by perfect squares. So you always have to divide by perfect squares. So if you don't know your perfect squares, make a list. So 2 squared, 4. 3 squared, 9. 4 squared, 16. We don't give you those. Actually, ironically, on your final exam, you'll have the perfect square chart and perfect cube chart. You're given that actually in 20-2. The minute you go to grade 11 or 20-1, you're not given that. You need to know it. So we need to practice them, remember them, okay? You can use your calculators, guess and check. It's all good. All right, so root 45. We're going to notice that it divides by 9 evenly, 9 times 5. So we always start with our perfect square on the left because he's the one that's going to become the coefficient. We're solving him. And then root 5. They multiply together. So, cross off root 9. He solves and becomes the digit 3. The root 5 slides beside him. And now you've got a mixed radical. So now what we do is we take a look at the radicands. So we need to remember the parts of our radical. So, the 3 is now the coefficient, and the 5 is the new radicand. The radicands are under the root sign, okay? So, back to mathing. We now have our mixed radical. Now we're going to take one, what if there's a number already in front? So we're going to do one with a mixed radical that can reduce even lower. So, example 2 is going to have 3 root 32. 3 root 32. Now, 32 can divide by a couple perfect squares. It can divide by 4, but it can divide by an even bigger one. 16. Good. So, root 16 times root 2. Now this 3 that's outside, he's connected, so he has to stay connected. Connected means he's multiplying because he's sitting side by side, so he's multiplying to those numbers. Now the square root 16, we're going to solve him, so we're going to cross him off, literally cross him off. And now we're going to write everything we need. So I need my 3. 16 solves and becomes a 4, and then I stick my root 2, I slide it beside. The last thing I need to do now is to multiply the 3 and the 4. So this is now going to give me 12 root 2 final answer. Okay? So you're going to notice on many of your multiple choice questions, and this is what caught some of you on your first final exam, or your first unit exam, is some of you, because remember, if it's multiple choice question, they're going to have answers that are only partly reduced, not fully reduced. Okay? So perhaps they did this question, but maybe the person did this question and divided it by root 4. So we could do this. We could have root 32, and if we did it with root 4 times root 8, 3 comes down, we solve and get a 2, these guys multiply. So we could get another multiple choice possibility as 3 root 8, or sorry, 6 root 8. But 6 root 8 is not fully simplified. Root 8 can still divide by root 4 again. So this could be a possible answer, and many people will pick it. How come? Because they think it's the final answer. You can go lower. You have to simplify your radicand as far as you can. Okay? So final answer, 12 root 2. Okay, so that's changing and converting entire to mixed. Now we're going to go backwards. We're going to go mixed to entire. So this is B mixed to entire. These ones are kind of fun. I like the mixed to entire better myself personally. I think they're more fun. So, example 1. Let's take 6 root 3. 6 root 3. So, what this actually is, we want the 6 to go under the root sign. Who remembers the rule to make the 6 go under? Lindsay? Exactly. So right here we have the index. We're going to use that index as an exponent on the number coming in. Or just write that number that many times. The same number of times as the index. So you could go 6 squared times by the 3 that's already under there. Or you could write it as 6 times 6 times 3. Okay? So, how are we going to get that answer? What are we going to do? We actually literally just multiply it in our calculator. So our final answer is going to be root, how big? Wait. Root 108. Okay, we have square root 108. Philip, put your phone down. Your fake phone. Yes. Yes. Okay, so now what we're going to do is we're going to put another one in there, but now we're going to put a cube and we're going to throw some fractions in there. So, example 2. Every time we add a condition, we're adding difficulty to the question. So we would consider number 1 an easy question. We're going to do a medium question now. So let's go with 2 cube root 7. 2 cube root 7. So now my index, I actually see my index, whereas on the other one, the index hides. So the process is the same. We're going to have 2 cubed times 7. And don't forget to put your cube root sign in there. You need to have that in the check mark part of your radical sign. So 2 cubed is 8. 8 times 7 is how big, guys? 56. So our final answer is cube root 56. Okay? Cube root 56. All right, so that would be about a medium difficulty question. Now we're going to do a standard of excellence question. The standard of excellence question, all it does is it throws a fraction in there. It's the only difference. Okay? So example 3. Okay, so a standard of excellence question we're going to have with a fraction. So we're going to go 2/3 cube root 4. Now there's a whole number under the radical sign, and there's a fraction that's going to go under. When one of them is in a fraction form, you must put the other number in the fraction form. So the first thing I'm going to do is I'm going to convert the 4 into 4 over 1. Okay, there's my first step. I need it all in fraction form. Now I'm going to take my 2/3, and how many times should I write my 2/3? 3 times. Good. So I have 2/3 times 2/3 times 2/3 times 4 over 1. Now, the rule is you multiply all your top numbers together, you multiply all your bottom numbers together, and then that's your new fraction. So, we write our cube root sign again. And we've got, I think, 32 on top. Somebody check my work. Okay, and on the bottom, what do we got? 27? All right. So we should get cube root 32 over 27. Yes. Yes. So this would be our entire radical. But remember, it is fractions. So we want to reduce our fraction at all times. So what you would do in your calculator, you're going to take your calculator, and we are going to take 32 divided by 27, and we're going to math bracket. So math, enter, and see if it has another lowest term answer. It doesn't. So that means it is in reduced form. Okay? But we always check with our math bracket. Okay, so final answer, we're good to go. So that's converting forms. The next thing we need to be able to do is deal with variables. How do we convert forms if we have variables? That's going to be a kicker here. So that's our next section. Is this number 3? Okay. All right, number 3, variables. So if we deal with variables as part of our radicand or as part of our coefficient, we have to remember that you take out groups of the index. That's the main important point, is when we're reducing them, taking them from entire to mixed, we want to divide out the grouping of the index. So we break the variables down into groups of the index. So let's do an example of that so you know what I'm talking about. So we're going to go root x 5. Root x exponent 5. Did you get better? All right. So first thing we do is we need to break it into groups of our index. What's our index that's hiding? 2. The index is a 2 that's hiding. So what we're going to do is we're going to put our big root sign on, and now we're going to break the x into 2's. So I can have x squared. Now we got to add to 5. How many more do I need? 1 more. Good. So we've broken it up into the groups of the index. Now we take out these groups. They're the ones that are going to come outside. So on the outside, I'm going to have x exponent something, root x exponent 1. The 1 can hide. Now, how do I know what my exponent is on the outside? Exactly. It's how many groups came out. So how many groups of 2 came out? 2. So it's 2 on the outside. So whenever we've got a variable underneath the radical sign as a final answer, we need to put a restriction. So our restrictions go as this. So this will be our final answer, but now we need to talk about restrictions. Okay? So, restrictions. Yes. When do we have them? Only when we've got variables under the radical sign. Okay? Only when you have variables under the radical sign. That's the only time we have restrictions. So if all of those x's came out, then we would have no more root sign. Sometimes that happens. If that was x exponent 4 on outside, or sorry, out underneath, we wouldn't have to worry about it because it would all come out and the root sign would completely disappear because what would be left? Square root of 1. And we can solve a square root of 1. It's 1. Okay? So we need a restriction when? Only when we have stuff under the root sign. And how do we start a restriction? Okay, so how? Well, you always take the radicand, and I want to write the entire, not just the variable, the entire radicand. So if it was 5x, you take the whole 5x. So you take the entire radicand and make it into an equation where it is greater than 0. That's how we set it up. So that's our important step. So we're going to write that down and we'll do the example like we saw. Yeah, move it up a little bit. Did I move it up too high? No?
Try this top.
So you take the entire radicand and you make it up into an equation where it's always equal, greater than 0. So, here's the example we did. We had root x to the 5. Now, in the end, I ended up with x to the 1. So it's the solution that we take this, our restriction from. So it's actually x to the 1 I'm doing a restriction on. So I take my x out of the radical sign, and I make it greater than 0. Now what I would do, if there is a coefficient in front of x that's other than the hidden 1, if there's anything sitting out there except for that hiding 1, I would divide it out. And then that would be what the answer would be. Now, is 0 divided by a number anything? It's always 0. So most of the time it'll be 0. But sometimes we have, under radical signs, we have something added or subtracted to this. And I'm going to show you another example like that. Okay, I'll just give you a second to finish writing that down. All right. So, here's another example. If it was root x minus 3, okay, I want to do a restriction. Well, right now, x minus 3 is simplified. How do I know if it's simplified? Because I can't take any groups of x out, because it's got a hidden 1 on it. I need a minimum of 2 on the exponent to come out, and there's not enough. So he just stays in there. It's already simplified. So now what I've got to do is I take it out of the root sign, x minus 3, and I make it always starting like this, greater than 0. Actually, it's going to be greater than or equal to 0. Because things can equal 0. Can you take the square root of 0? Yes, it's 0. Can you take and divide by 0? No, that's the only thing you can't do. You can't divide by 0. So now I'm going to literally solve. So if I solve this, it's a normal equation. Pretend that's an equal sign. I'm going to take my 3 over, so I'm going to add 3, and I'm going to add 3. So I get x greater than or equal to 3. So that means under my root sign, the x has to solve. If it was an equation and I had to solve it, the x number has to be 3 or bigger. Because if I put a 2 there, I get a negative number under my radical sign. And am I able to take the answer of a negative? Not for a perfect square, not for a square root, no way. Can you do it for a cube root? Yes, you're allowed to with a cube root, not with a square root. Okay, so there's our restriction. We're done. But sometimes there's numbers in front of x. What if it's a negative? Let's take a look at a negative example. So if we've got root negative 2x. Let's just put negative 2x. Let's do that. All right. I'm not going to put any other numbers. Yeah.
Wasn't it a thing where you can have a negative?
Right. But you can have a restriction because we don't know what x is. So if I can't have a negative under there, what do I have to multiply to a negative to make sure it ends up being a positive? Another negative. So that means x has to be a negative number here. So in order to work, in order to be possible, x must be a negative number. Okay? In order for that to work, x has to be a negative number. And we're going to show you how that actually works. So, I would take my negative 2x out of the root sign. And like we said before, we start greater than or equal to 0, always. Okay? Now, when something's sitting beside it, that means multiply. I'm going to do the opposite, and I'm going to divide to solve for x. So if I divide out the negative 2, if we remember, dividing by a negative does something funny to this sign. What does it do to that sign? It flips it. So now, my answer is going to be x, and I have a 0 over here still, but now my sign points the other way. And when it's pointing this way, that's telling me this, that x has to be below 0. It's got to be a negative number, or exactly equal to 0. Because 0 times anything is 0. And I can take the square root of 0. It's 0. So it can equal 0, or it has to be a negative number. Okay? So that's one of the rules we have to remember. If we divide out a negative in front of x, then that means we flip that sign. Okay? So our sign changed directions. And it's because x has to be a negative number. Okay? So that's the only time we have restrictions. Now, we only have restrictions under radical signs with even number indexes. So that means with a square root, or a fourth root, or a sixth root. So our cube root's going to have restrictions. No, they don't have an even index. Their index is 3. So cube roots do not have restrictions. Okay? And we're going to make that note. So, cube roots do not have restrictions. Because the only reason we have restrictions is because we worry about that negative under the root sign. That's the only reason. And we are allowed to have negatives under cube root signs. Okay? Because it's all about the number of factors. With a square root sign, there's 2 factors that have to be identical. Well, there's no way you're going to get 2 factors identical to give you a negative answer. There's 2 identical positives, give you a positive. 2 identical negatives, give you a positive. So if they're opposite signs, that's when you get a negative answer. Okay? Next, we are now going to add and subtract them. So, is this number 4?
Yeah.
Yep, okay. Adding and subtracting radicals. So we're going to add and subtract radicals.
So your roots don't have to have the x equals 0.
Nope. Nope. They're XER. X can be anything.
And that's with every odd number.
Odd number index. Yep. So a third cube root or a fifth root. Okay. Adding, subtracting radicals. There's only 2 things we need to have. What 2 things must we have in order to add or subtract? Who remembers? 2 things only. So we call that, starts with I. Say index. Same radicand. Okay? So 2 conditions in order to have this possible. You need to have the same index. And you need to have the same radicand. And all you do is we add or subtract the coefficients. Subtract coefficients only. And that's after each is reduced to simplest mixed form. Okay, so you need a simple mixed radical form. Okay? Okay, so we need a couple conditions. Same index, same radicand. That's how the conditions we need in order to add or subtract. And we only add or subtract the coefficients. That's the numbers in front attached to the radicals. Okay? I'll just move this up a little bit for you. So we add or subtract the coefficients only, and it's after we reduce everything. So our very first step, so the first step, reduce all. Reduce all radicals to simplest mixed form. Okay, so that always has to be your first step. Second step, match the radicands. Because you can't just add everything and then add the radicands. That's not how it works. What you do is you match the radicands. Once you've matched them, you add their coefficients. Okay? And then you write your final solution. And we'll do an example right away. Example. We're going to take root 50 minus root 8 plus root 18. So none of them are reduced. We must reduce them. So that is our first step. So we take a look at our perfect squares. The perfect square gets written first, 25 times root 2. Make sure you put the root signs on them. The root signs belong there. So root 25 times root 2. Which one solves? The 25. Good. So we're going to cross off the 25. And what does he become?
5.
Good. So we have 5 root 2. Perfect. Now we're going to look at root 8. What does root 8 divide by? 4 and 2. Good. So we're going to have root 4 times root 2. We're going to solve root 4 to become 2 root 2. Then we're going to take root 18. 18 divides by 9 twice. So root 9 times root 2. Please put the root signs on. Solve root 9. It becomes a 3 root 2. Now I got to go back and put my plus and subtract signs that are separating my radicals. So I'm going to put a subtract there and a plus there. And now all I've got to do is I have to add the numbers in front. You just add or subtract left to right. So what it means by our second step, meaning match the radicands, we look at all the radicands and see if they match. If they're all identical, that means they match. That means I can add or subtract the numbers in front. Now, if there was another one added here that had a different radicand, he'd be by himself. I could not add him to the rest of these because he had a different number. So, these numbers, I'm going to take 5, subtract 2 is 3, add 3 more, gives me 6 root 2. Now we're just going to pretend for a moment. We're going to pretend for a moment that at the end of this question we had a plus root 3. Let's just pretend I have a plus root 3. Could I add the plus root 3 to my root 2? No, because they have different radicands. So this plus root 3 is just going to stick on the end. Okay, it would become part of the answer, but you couldn't add it to the other guy because they don't match. Okay? Any questions so far? Okay, now we're going to multiplying and dividing. So, is this number 6? 5? Okay, multiplying. Multiplying radicals. These ones are super easy, I believe. All you're going to do is, we have to have one condition. One condition, in order to multiply, you have to have the same index. Okay, you need to have the same index. So, what do? We multiply So how do we do it? We multiply radical or radicands together. Then multiply coefficients together. Final step, what do you think? Final step was always just like fractions. Reduce. You need to reduce to simplest mixed form. Okay, so reduce to simplest mixed radical. Okay, once you got that written down, we're going to do a couple examples and see how you do. Yep, and I'll let you know that next week on Tuesday, our final day, we'll go over the in-class final, and then I'll tell you what your final is built on, how many questions per unit. Absolutely. Okay, so multiply. Here's our example. You ready? Almost, stepping away. Okay, example 1. We're going to have 4 root 5 times 2 root 2. We're going to multiply coefficient to coefficient and radicand to radicand. So we're going to get 8 root 10, and root 10 does not reduce. Okay? So that one is in final simplest mixed form. The next one we're going to do is going to have a fraction in it. Let's go with 2/3 root 6 times 4 root 2. 2/3 root 6 times 4 root 2. So, the coefficient on the left is in radical form, or sorry, fraction form. So we need to make that 4 into fraction form. So I'm going to put it 4 over 1. Now we're going to multiply top to top and bottom to bottom for those fractions, just a simple fraction rule. Or if you want it in your calculator, you could simply just go bracket 2 divided by 3, 2/3 times 4. You can do it in your calculator. And then you can math bracket, math, math, enter, enter. You get 8 over 3. So we can do it in the calculator and reduce fraction. So 8 over 3. So this is going to give us 8 over 3 root 12. Now we know that root 12 can break down. 12 divides by root 4. So the 8 over 3 is going to stay outside. Root 4 times root 3. That's what 12 breaks into. We're going to solve the root 4, but it's a fraction again on the outside. So root 4 is going to change to a 2 over 1. The 8 over 3 is sitting beside it, and we're going to multiply. The root 3 comes and sits beside the fractions. The final answer is to multiply the fractions outside. So we're going to get 16 over 3 root 3. So that will be considered a medium question. The next two we're going to do are like foiling and distributive law. You still have to FOIL and do distributive properties. Okay. Example 3. Okay, I'll give you a sec to finish writing that down. Okay, we are now going to distributive property. So this is example 2? 3. Okay. Example 3. 6 root 5 times 2 root 3 plus root 5. So this one, you could do two ways. You just do simple distributive property. He multiplies to both. Or if you like to do the box method, it's a 1 by 2 box. So I like the box method. I'm doing it by the box. So 2 root 3 goes here. Root 5 goes here. 6 root 5 goes out front. Now you do the same thing that you would do for normal multiplying. We're going to multiply coefficient to coefficient, radicand to radicand. So we're going to take 6 times 2. That's going to give us 12 out front. And then we're going to take 5 times 3. That's going to give us root 15. Okay? So that gives us 12 root 15. The next one, I have a positive 5 and a hidden 1 in front. So that 1 is multiplying by the 6, and 5 is multiplying to the 5. So I'm going to get 6 root 25. What do we know about root 25? Yeah, it's a perfect square. So he reduces completely to become a 5. So now you've got to multiply those two numbers. So it's going to become 30. Now, the number's all by itself. There's no more radical sign. It completely disappeared on this one, and that's okay. Now we've got to rewrite our answer outside the boxes. So my final answer for this would be 12 root 15 plus 30. You can put the 30 out front as well. You can go 30 plus 12 root 15. Okay, it doesn't matter the order you write them in. So that's distributive property, a 1 by 2 box. The next kind is a 2 by 2, where it's going to be foiling or area box. Okay? So we'll do one more example like that, and then we're switching to dividing. Hey, example 4 is coming at you. Okay. So we're going to have 2 root 3 plus 4 root 6 times 5 root 2 minus 3 root 2. No, not 2. Sorry, 2, 2. Let's find another one that's good. Oh, let's go 8. There we go. So this one I'm doing in an area box. If you are a foiler, you will foil. So I have 2 root 3 and a positive 4 root 6. I have 5 root 2 here and a negative 3 root 8. We're going to simplify in the box. So first thing I'm going to do is I'm going to take my 2 times my 5, and that's going to give me 10. Then I'm going to take 3 times 2, and that's going to give me root 6. So now I get 10 root 6. And I check on my perfect squares. Does root 6 divide by root 4? Not without giving me a decimal. So that means that that one is fully simplified. Now I move to the next one. I'm going to take 2 times the negative 3. That's going to give me negative 6. And then I'm going to take the 3 times the 8, and that's going to give me root 24. What do we know about root 24? It can be reduced by root 4. Root 4 times root 6. So root 4 times root 6. As negative 6 comes down, we're going to solve root 4 to a 2. What do I do with that 2 now? What am I going to do with that cute little 2? Nice. I times it to the negative 6 because they're sitting side by side together there. I'm getting tongue-tied here. So that's going to give me negative 12 root 6. That's a 12 there. Negative 12 root 6. All right, so I have a couple root 6's on top here I can add, but I'll add those later when we're done. Now we're going to go to the next part. So my next part now, I'm going to fill in the bottom. So I'm going to take my 4 times my 5 to give me 20. I'm going to take my 6 times my 2 to give me root 12. Does root 12 reduce? Yes, 4 and 3. So we're going to have root 4 times root 3, and the 20 slides beside. Who solves? The 4 does. So we're going to solve root 4. He's going to become a 2. No, I don't want it off. And so now, I don't know why it turned off. Pause. Okay, so let's just take a look there. We had a little glitch in the system. So back to this, we're going to end up with 40 root 3 for that question. Now we're going to move to the next part. So I'm going to take 4 times the negative 3. That's going to give me negative 12. Then I'm going to multiply the radicands and get 6 times 8 is going to give me root 48. Now root 48 for sure will break down. It's going to divide by root 16. So negative 12 will slide down. Root 16 times root 3. All right, now the 16 is going to solve and become a 4. And like we did before, we're going to multiply the 2 coefficients. So that's going to give us a total of negative 48 root 3. So in this case, now in the end, we have to match the ones that are like terms. So we've got some root 6's that we can add the coefficients that match, and then we've got some root 3's that we can add the coefficients. So we're going to string all the answers out in a row here. So our final answers would look like this before we combine them. So we're going to have 10 root 6 minus 12 root 6 plus 40 root 3 minus 48 root 3. Now I've color-coded them on purpose because I've matched them up. Now, we're going to take and we're going to add the coefficients. So again, back after we multiplied, now we're just adding coefficients of the ones that match. So the root 6 will not change. I add my coefficients. I have a negative 2 out front. Over here, my root 3 will not change. All I've got to do is add my coefficients, 40 and negative 48. That's going to give me a negative 8. So we end up with both negative coefficients, our final answer after we have combined them. Okay, check your work. Now we're going to move on to dividing. Okay. So this is going to be number 6, dividing. So number 6 is dividing radicals. So we straight up, again, we need to have a condition, and there's only one. We have to have the same index, just like multiplying. So, same rules as multiplying. coefficient divides by coefficient. Spelled it wrong on top. So, coefficient divides by coefficient, and radicand divides by radicand. Divide line. Okay, here's an example. So we've got 4 root 27 divided by 2 root 3. Now myself personally, I would write it as fractions straight up and down. So I would rewrite this as 4 root 27 divided by 2 root 3. And now they're lined up perfectly for me to divide. So I'm going to divide my coefficients and I'm going to divide my radicands. So this is going to give me 2 root 9. Ironically, root 9 is a perfect square that we can solve, and he'll become a 3. So now we're going to multiply our coefficients. We end up with a 6 root 1, and the root of 1 is just 1. So our radical disappears completely, and our answer is 6. Okay? Now, if there's more than one item on top, make sure that you divide by all of them. So, for example, you could have let's start with some, we'll do these. We'll go with 5x root 6x times 4x to the 4 root 3x cubed, all dividing by 2x root 2x cubed. All right, first things first, we have to multiply the top so we can simplify it into one fraction. So we're going to multiply coefficient by coefficient, and then we're going to multiply radicand to radicand. All right, so we're going to get 20x to the 5 root 18x to the 4, all divided by 2x root, under the root sign, 2x cubed. All right, when we have variables and we're dividing variables, we subtract exponents. So here, I'm literally going to divide. Right here, I'm going to subtract exponents. Don't forget there's a hidden 1 on that x. Okay? Okay, we're going to do the exact same thing under the radical sign. So I'm going to take 18 and divide it by 2, and then I'm going to subtract my exponents. So let's start here, left to right. 20 divides by 2, 10 times. x5 subtracts x1 and gives me x to the 4. Under the root sign now, the radical sign, I'm going to end up with 9, x exponent 1. Well, what do we know about 9? Well, first of all, we know 9 is a perfect square. So we've got 10x to the 4. We're going to break this guy down into root 9 times root x to the 1. So root 9 is a perfect square. We're going to solve him. He becomes a 3. Our 3 is going to multiply to that 10. So we're going to end up with 30x to the 4 root x. Now remember, we have an x under the radical sign, so we have to now do our restriction. So our restriction, again, we take x and make it greater than or equal to 0. There's nothing in front of x except for a hidden positive 1 that I would divide by, so I have my restriction immediately. Okay? So our final answer must include your simplified radical and the restriction, if there's variables. Now, what if the x came completely out? Do we still have to include the restriction? Yes, we do. But if it comes out completely, so for example, let's say I had this under the root sign, completely different example. Let's say I had 5x cubed root 2x squared. Let's say that. 2x squared. So we know that root 2 will not reduce, but x squared will. It is a group of 2, and I can take it out. So I am going to take it out. And what I do is I add one group that comes out to that x to the 3 at the outside. So I'm going to get 5x to the 4 root 2. Now, since my final answer doesn't have a variable in the radical sign, I then say there's no restrictions. No restrictions means x can be any real number. You must include the restriction. So this is our restriction. So, again, our restriction is that there are no restrictions, but we must state that by saying XER. Okay, so that's dividing radicals. Now, our second last thing we're going to look at is rationalizing. So, number 7 is rationalizing radicals. Well, when do we rationalize radicals? Well, we rationalize radicals when we can't divide them. So when we can't divide the radicands without getting a decimal. So that's what happens there, without getting a decimal. Okay, so that's when you do it. Are there any conditions we need to worry about? Well, the only condition, again, is it's got to be the same index. Okay, that's our condition. So, let's start with our example now. So, example, 15 over root 5. Well, there's no radical on top for root 5 to divide by, so we're rationalizing right away. Now, when I rationalize, what that means is I take the radical on the bottom, but I make sure it's reduced. So that's something we also have to write before our example, is we also have to make sure the denominator is in simplest mixed form. Mixed radical form. It must be in simplest mixed radical form when we do it. Now, something else we have to note, when it is in simplest mixed radical form, we also have to make sure that we only multiply the fraction, meaning top and bottom, both top and bottom, by the radicand. This is going to make the radicand on the bottom become a perfect square, which we can solve. So, let's take a look at this before we actually look at our example. So, if I were to take, for example, root 2 times root 2, well, that's going to give me root of 4, which is a perfect square that solves to become positive 2. So if you notice, if I started originally with a positive root 2, and I times it by itself, the root sign disappeared in the end. So the root sign completely is gone because we solved the perfect square. By rationalizing the denominator, that means we don't want run-on decimals on the bottom, which means we don't want non-perfect squares on the bottom. That's why we have to rationalize. So, I'm going to take my first example here, and I'm going to multiply it by root 5 over root 5. We also know that any number on top of itself is 1. So I'm not changing the value of the equation by multiplying by 1. So that's why this also works. So the 15 up top doesn't have a radical to multiply by, so the 15 is just going to slide beside and become the coefficient. Here we're going to multiply them and get root 25, which we're going to solve, and that's going to become 5. So our denominator becomes a 5 by itself now. And our top is 15 root 5. Okay? Now, can we simplify that further? Well, yes we can. So, how can we reduce that? Well, we need to be able to make sure we get the same decimal. So let's type it in and see what we get for a decimal. So 15 root 5, enter. Divide by 5, enter. We need to get 6.7. So let's say I divided 15 by the 5 and got a 3. Is 3 root 5 the same answer? 6.7. You bet it is. So what have we just done? What we've done is we've simplified these. The coefficient and the denominator can simplify. 15 divides by 5 3 times. So our final answer is going to look like, let's move this over a little bit. And we're going to move you guys over a little bit. Nope, not that one. This one. There we go. Times root 5. Okay. So the 15 is going to slide beside the 5 there. That's what was happening. So I just need a little bit more room there. So now that's going to give me 3 root 5. And like we showed on the calculator, we get the exact same answer. So now we have no more denominator. The denominator has completely reduced and disappeared. So that's how we rationalize. As long as we follow all of our steps, we are good to go. Okay? Now how do we rationalize with variables? We would do the exact same thing. The variable would multiply so that we could reduce the variable. Okay? Let's do an example of that. Here's a variable example. So let's go 10 letter P root 6 all over root 12P. All right. So we need to break down 12 because 12 is not in reduced form. So we're going to break him down to become root 4 times root 3P. Okay? Now, P doesn't break down because he has a hidden 1, and we can't divide out a group of 2. There's not enough P's. So the P will have to stay under the root sign. Now, root 4, it does solve. He's going to become 2. So we're going to have 2 root 3P. So this becomes, our top stays the same, 10 P's, root 6, all divided by 2 root 3P. So, can I divide anything? Well, there's nothing that we can divide up top. So, for example, the 10 and the 2 divide instantly, of course. But 6, yes, it divides by 3, but there's no P for it to divide by on top. So that means, what am I going to be using to divide by on top? This right here. That's what I'm using. So now, let's just move this over here. I'm going to have 10P root 6 all over 2 root 3P. And I'm multiplying now by root 3P over root 3P. That's going to become, when I multiply these, it's going to get rid of the radical sign, and basically 3P stays. Why? Well, I'm going to bring it over here, and I'm going to show you right here. So what actually happens is this. So 3P times 3P becomes 9P squared. But that's under a root sign. They're both perfect squares. 9 solves to become a 3, and P squared comes outside because I can take one group of 2. So it becomes P1. So if you take a look, that's our radicand. So if we get used to this, we can just basically take off the root sign, and that's what I would multiply to my bottom. So our next step then is 10P root 18P, because I'm multiplying these guys, all on top of 2 times 3P. Okay, I'll give you a minute to write that down. Okay, so now, on the bottom, this is going to become a 6. Okay, so I'm just going to erase this, or actually I'm just going to move it over. We're going to clone that. Oh, we're going to move it over here. So, that's what we ended up with. So now, we're moving it over here. And what's going to happen? Well, the 2 times 3 becomes a 6. And now what I'm going to do is I'm going to reduce them. Well, P1 and P1 can subtract and disappear. I'm not able to reduce the P that's under the radical sign. I could only do that if there was another radical, and there's not. That was the whole point, we reduced them. Now what I'm going to do is I need to reduce the 18, because 18 can still break down. So, coming over here now, I'm going to have 10 root 9 times root 2p, all divided by 6. Well, root 9 is going to solve and become a 3. And 3 is going to multiply to the 10. So this is going to end up becoming 30 root 2p all over 6. Now, the only thing that can reduce, again, we are not looking at the radicand because there's no radicand on the bottom. So that's why we didn't do anything with the radicand there. The only thing I can do is see if these coefficients and the denominator reduce, and they do. 30 divides by 6 5 times, so it's going to become a 5, and we will no longer have a denominator. We're just going to have 5 root 2p. Again, we need our restriction. So our restriction, we're going to take p out of the root sign, 2p, because there's 2 with it. And again, we make it greater than or equal to 0. And we solve for p. Well, if I solve for p, I'm dividing by 2. 0 divides by 2, but 0 divided by anything is still 0. So I'm going to get p is greater than or equal to 0. So that's my restriction that I need to include as part of my answer. So my final answer right here, I am now going to include my restriction. You'll include it with a comma. So now I'm going to say p must be greater than or equal to 0 in order for that to work to be true. So that's how we deal with variables and rationalizing. Our last step is to deal with solving radical equations. Finish. Keep some here. Okay. So here we go. So the last one, I think this is number 8, solving radical equations. EQNS is my abbreviation. Solving radical equations. So, first thing we have to remember is because there's variables under the root sign, that's what we're solving for, we must do a restriction as well. So, our first example is going to be root 5 subtract x equals 3. So, what are the rules? First rule is you need to make sure the radicals are on the same side. So move radicals to the same side if possible. Okay, that's first step. Well, we only have one radical, so we don't have to worry about that. Second step is to add like terms if there are. Third step, we are going to now square both sides. Using brackets, and this is super important. Using brackets. The brackets and the square are going to get rid of the root sign because they are opposite functions. And then our fourth step is literally just solve for x. And solving for x, we need to also state the restrictions. Okay, so let's do all those steps. So, move radicals to one side. Well, number 1 and number 2 don't apply to us with this example. This would be considered an easy example. So we're right on number 3 right now. So now we go to brackets and square both sides. Brackets and square both sides. Brackets are super important because if you have a negative, they will square the negative to become a positive. Now, on the left-hand side, all it does is get rid of the root sign because it's opposite functions. So now we've got 5 subtract x equals 9, and we literally solve for x. So I'm going to move the 5 to the right, subtract 5 to both sides. I'm going to get negative 1x equals 4. Now I need to divide out what's in front of my variable, negative 1, because the only thing you want in front of your x is a hidden positive 1. That's when you know you're done. X equals negative 4. Okay, now we have to go state our restriction. We solved for x. We have to state our restriction. And then we also have to, I forgot to mention, our last step is to check our solution. We have to check if the left side equals the right side, because if it does, it's a true solution. If it doesn't, it is not a true solution. So, here we go. We are now going to state the restriction. So, stating the restriction, I need to take the variable out of the root sign. So I've got 5 subtract x, greater than or equal to 0 is how we always start. I'm going to move my 5 to the other side, subtract 5, that wipes the 5 out. So I'm going to have negative 1x greater than or equal to negative 5. Now I'm going to divide out negative 1, divide out negative 1, and we get x is positive 5. Now, when we divide by a negative, that sign's going to flip directions. So that's saying the condition is the variable must be equal to 5 or smaller in order for this to be a true solution. So now we're going to do the check to see if it is a true solution. So we got for a solution, we got x is equal to negative 4. So now we need to check the solution. Check left side, right side. So we write our equation, root 5 minus x. That's our left side. Our right side was a positive 3, I believe. Yes, 5 minus x and positive 3. So we've got our left side, we've got our right side. Now we plug in x. So I've got root 5 subtract, and now when you substitute, you must use brackets. So we got x is a negative 4, and then over here we've got a 3. So now, under our root sign, 2 negatives in the middle together will turn to positives. I get root 9. We know that root 9 solves and becomes 3. So my left side is equal to my right side. That means it is a true solution. X is negative 4. And remember, it meets the condition we had before. The condition said it had to be the digit 5 or smaller. And negative 4 is smaller than 5. So we did correctly. All right, so if we want to try 2 more examples here. So, example 2 for our equations. So what if we've got coefficients or numbers on the other sides? So for example, what if you had something like this? Root 6y minus 5 plus 2 equals 0. Well, in this case, we need to take the 2 to the other side. So we're going to subtract 2 and subtract 2. So we're going to get the root 6y subtract 5 is equal to negative 2. Now we've isolated the radical sign, which you're supposed to do. Isolate the radical. Move them to both sides and isolate them. Now we square them with brackets. Here we've got a negative sign, so it's super important that these brackets are here. So now I square it. All it does is get rid of the root sign on the left-hand side. So on the left-hand side, all I'm going to have now is 6y minus 5. And on the right-hand side, I'm going to have a positive 4 because I squared a negative. Now we solve for y. So I'm going to move my 5 over by adding 5. I'm going to get 6y is equal to 9. And now I divide by what's in front of my variable. So y is equal to 9 over 6, which I'm going to reduce. They both divide by 3. So I'm going to get 3 over 2, which is 1.5. It's an exact decimal, so we can use the decimal. If it was a run-on decimal, we would use the fraction. So now we need to check our solution, and we need to do our restriction. So let's do our restriction. We take what's under our radical sign, remove it from the radical. So we've got 6y minus 5, and we start greater than or equal to 0. We're going to move our 5 over, So we're going to add 5 to both sides. We're going to get 6y is greater than or equal to positive 5. Now we're going to divide out the 6, divide out the 6. So this is telling us the condition that y must be greater than or equal to 5 over 6. Okay, that's our condition. Well, we got an answer that's bigger than 5 over 6. We have 3 over 2, 1.5, so we met the condition. So now we actually have to do the check, left side, right side. So I'm going to rewrite the equation. Root 6y minus 5 plus or equals negative 2. So equals negative 2. Or we could use the original equation. Let's use the original one. Plus 2 equals 0. So we would draw a line. We've got our left side, our right side. So now we're going to stick in the answer for y. So still under the root sign, y is a fraction, so I'm changing 6 to a fraction. 6 over 1, and we got y, which we get for y as an answer, 1.5. So 3 over 2. So we got 3 over 2. Subtracting 5, all under the root sign. Then plus 2. We want it all to equal 0. So we've got fractions, so we have to multiply tops, multiply bottoms. So we're going to get 18 over 2. 18 divided by 2 is 9. So then we're going to get root 9 minus 5 plus 2. That's going to give us root 4 plus 2, and the root of 4 cancels and gives us 2. So we have 2 plus 2. Well, that's going to give us, it's going to give us 4, not 0. So we end up with our left side is not equal to our right side. So what we say is, it is not a true solution, it is an extraneous. It's an extraneous solution. It's not a true solution because the left side did not equal the right side. This concludes our review of radicals, Unit 1.